Continuing on with the Organic Chemistry 1, Chem 112 lecture series, we're now going to be discussing Chapter 9, which is a foundational chapter in organic chemistry and organic synthesis. Chapter 9 focuses on substitution and elimination reactions, and we're going to also discuss alkyl halides and the properties of alkyl halides. So first things first, let's introduce a major functional group that we'll be seeing a lot in this chapter, and that is the alkyl halide functional group. So what are alkyl halides? Well, organohalides are organic compounds containing at least one carbon-halogen bond. They have a general formula of CnH2n plus 1x. The du is equal to 0 for each alkyl halide because we only have carbon-carbon and carbon-halogen single bonds. Now, when naming alkyl halides, halogens are indicated with halo prefixes. Bromo for bromine, chloro for chlorine, iodo for iodine, and fluoro for fluorine. To name an alkyl halide, you find the longest chain and name it as the parent chain. You number from the end nearest to the highest priority substituent. Importantly, halogens and alkyl groups have the same priority. From there, you identify and name the substituents, you number the parent chain, and you assign each substituent. In terms of a priority list so far, alkenes and alkynes are higher priority than halides and alkanes, while halides and alkanes are equal priority. So you choose the lowest locant number, and if there's a tie, then you go to alphabetical order. For example, this compound would be named 5-bromo 2,4-dimethyl heptane. The reason why we choose the numbering method in red is that if we compare the alternative numbering method, we would have a locant number of 2. And as we can see, 2 is lower than 3. So in this case, the methyl group, because it has the lowest locant number, we use the numbering method in red because it gives the lowest locant numbers sequentially. So this compound will be named as 5-bromo 2,4-dimethyl heptane. If we look at this compound on the right, we have two possible numbering methods. In this case, we have a locant number of 3 versus 2. We're going to use the numbering method in red. So this will be named as 2-bromo 4,5-dimethyl. And it's a 7-carbon chain, so it would be heptane. With these examples in mind, I'd like you to try to name the following compound. So take a few moments, pause the video and work through this example, and then we'll discuss. So in this case, let's look at our two possible numbering methods. We can number from left to right, or we can number from right to left. In this case, if we look at our two numbering methods, the numbering method in blue gives the lowest locant number of 2. So in this case, we have a chlorine at the 4 position and methyl groups at positions 2 and 3. So we'd name this compound as 4-chloro 2,3-dimethyl, and it's a 6-carbon chain, so this would be hexane. Okay, let's keep going now. And let's talk a little bit about alkyl halide nomenclature when you have multiple functional groups. You're going to number your carbons, so the highest priority group has the lowest locant number. The priority list so far is that alkenes are higher priority than alkynes, which are higher priority than halides and alkanes. So for example, if we're naming the following compound, we'd number this compound to give the alkene, the carbon-carbon double bond, the lowest locant number. So this would be named as 4-chloro 1-butene. Given what we've learned from this initial example, I'd like you to take a moment and try and name these next two compounds. So pause the video, work through these next two examples, and then we'll discuss. So in this case, we have a tie in locant number between the alkene and the alkyne. So we're going to choose the locant numbers in black because it gives the alkene the lowest locant number. Because if we have a tie between an alkene and an alkyne, the alkene takes priority. So we have a chloro group at the 4 position. So this would be 4-chloro, 1 hex, hex. I'm going to use the old school naming convention. Hex 1-ene 5-ine. In this case, the 1 denotes the position of the alkene, and the 5 denotes the position of the alkyne. Again, a key important point to be made is that in the event of a tie between an alkene and an alkyne, the alkene gets priority in terms of locant number. Looking at this next example, we have an alkyne and some other functional groups. We're going to number, so we have the longest chain, including the alkyne, and we're going to give the alkyne the lowest locant number. So this would be named as 4-chloro, 3-methyl, and it's 5 carbons, so it would be pent 1-ine. Or you can name it as 1-pentyne. That would also work. Wonderful. So we've named compounds containing alkyl halides and other functional groups. One thing that I would like to note, if there is a tie, you're going to assign the smallest carbon locant number to substituents in alphabetical order. For example, we have a choice between an ethyl group and a fluoro group. In this case, E is first alphabetically, so we're going to use the numbering method in blue. So this would be named as 1-ethyl, 3-fluoro, cyclohexane. With that example in mind, I'd like you to tackle these next two compounds and try naming these next two compounds. So pause the video, work through this example, and then we'll discuss. So in this case, we have a choice between giving the chloro or the methyl group priority. In this case, chlorine is first alphabetically, so we're going to give chlorine the lowest locant number because there's a tie. So this would be named as 2-chloro, 4-methyl pentane. By the same token, looking at this next example, we have a choice between a chloro and a bromo group. Bromine is first alphabetically, so we're going to name this compound as 2-bromo, 4-chloro, pentane. So if there's a tie, then you resort to alphabetical order because alkyl groups and halogens are equal priority. Okay. How do we go about preparing alkyl halides? One standard method to make alkyl halides is radical bromination. So N-bromosuccinimide can selectively brominate allylic positions when irradiated with light. So HV, that's the notation for light. So how does this work? Well, this goes via a radical mechanism, and this explains why bromination is selective for the allylic position, because it makes the most stable allylic radical. Again, this is a resonance stabilized radical. In terms of the mechanism, N-bromosuccinimide naturally decomposes to generate bromine in small concentrations. Once formed, the bromine can then fragment homolytically. So the bromine-bromine bond breaks, and we generate two bromine radicals. From here, the bromine radical abstracts a hydrogen at the allylic position to make our most stable allylic radical. And then that radical then reacts with an additional equivalent of bromine, either in Br2 or the bromine atom in N-bromosuccinimide, to form a new carbon-bromine bond and propagate the chain. In net, we've installed the bromine atom at the allylic position. Now, when we talk about the radical bromination selectivity, allylic bromination is selective for the most substituted position, which makes the most stable radical. As we discussed previously, the most substituted radicals are the most stable. Radicals can be stabilized via hyperconjugation. So with that in mind, let's try to apply what we've learned and draw a mechanism for the following reaction. And I'd like you to explain why product A is favored over product B. So with N-bromosuccinimide, you can, and you're free to, just use Br2 as your starting material because the N-bromosuccinimide in this case is just making a trace amount of bromine, and that's what's actually participating in the reaction. So pause the video, work through this example, and then we'll discuss momentarily. Okay, so first things first, we're going to get cleavage of the bromine-bromine bond to generate some bromine radicals. From here, we're going to abstract a hydrogen to generate the most stable, most substituted radical. Because this position is tertiary versus the secondary position, we're going to see product A form because the radical that leads to product A is the most stable radical. From here, we abstract a bromine atom, and that in turn yields our desired allylic bromination product A. So again, radical bromination favors bromination at the allylic position and the most substituted allylic position because that's the most stable radical. Okay, continuing on, let's now talk about nucleophilic substitution reactions. So if we think about an alkyl halides are polarized with the carbon halide bond. The carbon is electrophilic, And as a result, nucleophiles can attack and replace the halide in carbon-halogen bonds for many alkyl halides. So in this case, if you have a carbon-halogen bond and a nucleophile, that nucleophile can attack and displace your halogen via a substitution reaction. Now, nucleophilic substitution reactions are really important because they have a defined stereochemical outcome. This was shown early on via what's known as the Walden inversion, where Walden showed that you can take minus malic acid and convert it to plus malic acid using achiral reagents. The key takeaway is that nucleophilic substitution reactions invert the configuration at a given chiral center. This is the full Walden inversion. In the first step, you have a substitution, and as you can see, you observe an inversion of the configuration at your stereocenter. Treatment of the chlorosuccinic acid with silver oxide and water triggers a second inversion, a second substitution, where the chlorine is replaced with a hydroxyl group with inversion of stereochemistry. So let's talk about the SN2 reaction, which is one type of substitution reaction. SN2 stands for second order nucleophilic substitution reaction. So in the SN2 reaction, the SN2 reaction occurs in a single concerted step. Your nucleophile attacks your electrophilic carbon. The carbon halogen or carbon leaving group bond breaks, and we end up with substitution with an inversion of configuration. If you start with an S starting material, your product will have the opposite configuration after the substitution reaction. Now, what's the mechanism? The SN2 mechanism is a concerted attack of the nucleophile and loss of the leaving group. The nucleophile attacks your electrophilic carbon, you lose your leaving group. This occurs through the following transition state. Importantly, the nucleophile approaches from the opposite side of the carbon leaving group bond. It's known as the backside attack, and the reason why this occurs is if we think about your carbon halogen bond, this is your sigma bond. Behind the carbon halogen bond is the sigma star antibonding orbital, and that's what the nucleophile is attacking. So the nucleophile approaches 180 degrees from the carbon halogen or carbon leaving group bond. This angle of approach is going to be important later on. So here's a typical SN2 reaction. Let's practice what we've learned and let's draw a mechanism for this reaction. For the mechanism, you don't need to draw the transition state. I just want to see the arrow pushing steps. So pause the video, work through this example, and then we'll discuss. So in this case, our nucleophile is going to attack. The carbon leaving group bond breaks in a concerted fashion, and net we formed a new bond between the carbon and the nucleophile, and as a byproduct, we lose our leaving group. Notice that this occurs with inversion of stereochemistry. This is an example of a stereo-specific reaction. You start with a defined starting material, you get a defined product out. Okay. Let's talk a little bit now about the kinetics and reaction coordinate for the SN2 reaction. The SN2 reaction, as the name implies, is a second order reaction, which means the rate of reaction is dependent on the two reactant concentrations. The rate depends on the concentration of substrate and nucleophile. This makes sense, and this supports the reaction mechanism where the rate limiting step is a concerted attack of the nucleophile and loss of the leaving group. This rate limiting step is bimolecular. Wonderful. Now, the SN2 reaction coordinate is a reaction with a single transition state. The rate limiting step is bimolecular. This transition state involves formation of the carbon nucleophile bond and breaking of the carbon leaving group bond. One thing that I'd like to draw your attention to is that this transition state is sensitive to substrate substitution. The more congested your carbon leaving group bond becomes, the more substituted the carbon with the leaving group becomes, the higher in energy and the more difficult it is to reach this transition state for the SN2 reaction. Let's now talk about some factors that influence the SN2 reaction and the rate of SN2 reaction. So let's first talk about the nucleophile. What is a nucleophile? It is a neutral or negatively charged Lewis base that is electron rich at one or more atoms. The nucleophile donates a lone pair in the SN2 reaction. So the nucleophile is using its lone pair to form a new bond between a carbon atom and the nucleophile, and we kick out the leaving group. Nucleophiles can be neutral or charged. So let's practice drawing the mechanism and drawing some products with these next two examples. So in this case, this amine is going to be the nucleophile. We're going to attack the carbon with the leaving group. We're going to lose our leaving group. And that gives us the following substitution product. In practice, usually once these kinds of neutral nucleophiles attack, if they're protonated, usually solvent will come in and pull off this proton. They don't usually stick around in this positively charged state. Usually like another equivalent of starting material will pull off this proton. Looking at this next case, we have a charged nucleophile, but it's the same mechanism for SN2. You attack the carbon with the leaving group leaves, and in turn, we form a new bond between a carbon and our nucleophile. This is an example of a named reaction known as the Williamson ether synthesis. Now, we know what nucleophiles are, but how do we know what makes an effective nucleophile? Well, nucleophile strength parallels base strength and charge localization rules. In general, when it comes to charge, anionic species are generally more nucleophilic than neutral species. Hydroxide is more nucleophilic than water. The acetate anion is more nucleophilic than acetic acid, and so forth. So if we had a pair of two molecules and we had to select and circle the more nucleophilic species, the anionic species will be more nucleophilic. Which makes sense because there's more localized negative charge, more electron density on your nucleophilic atom. In terms of electronegativity, lone pairs on less electronegative atoms are more nucleophilic. So for example, a carbon-centered anion and a lone pair on a carbon atom is going to be more nucleophilic than a lone pair on a fluorine atom. So if we compare bromine and chlorine, bromine, or the bromide anion, will be slightly more nucleophilic than the chloride anion because bromine is less electronegative. For the halides, I would just note that the halides are a bit of a special case, and we'll talk more about them later on. If we had to compare an amine versus an alcohol, because an amine, the nitrogen is less electronegative, so this nitrogen atom and this overall molecule is going to be the stronger nucleophile. Again, lone pairs on a less electronegative atoms are more nucleophilic. Another factor that influences nucleophile strength is steric hindrance. Lone pairs on atoms with large steric congestion are less nucleophilic. The more substituted your carbons adjacent to your nucleophilic atom become, the less nucleophilic your overall molecule becomes. So for example, if we compare these two sulfur nucleophiles, the less substituted sulfur-based nucleophile, where the sulfur is attached to a primary carbon, is going to be more nucleophilic than if the sulfur is attached to a secondary carbon. Because this molecule on the right, if the sulfur is attached to a primary carbon, your nucleophile is less hindered. It can more readily attack the carbon with the leaving group. It's important to note, because the nucleophile donates a lone pair, delocalization and conjugation can have a huge effect on a given atom and a given lone pair's nucleophilicity. Lone pairs that are delocalized via resonance are less nucleophilic. That's why, for example, methoxide is more nucleophilic than the acetate anion, because the acetate anion lone pair is delocalized. By the same token, if we compare an amide and an amine, because an amide lone pair is delocalized, the amine is going to be generally more nucleophilic. So the SN2 reaction involves a nucleophile, and it also involves a carbon with a leaving group. So let's talk a little bit about the leaving group. The leaving group is the group displaced during the SN2 reaction. So when your nucleophile attacks your carbon and you break the carbon leaving group bond, the leaving group is the group displaced, the group that leaves during the SN2 reaction. Good leaving groups are weak bases that can stabilize and delocalize a lone pair. I would like you to note that the leaving group for the SN2 reaction must be bonded to an sp3 carbon in order to react in SN1, SN2, E1, and E2 reactions. So your leaving group must be attached to an sp3 carbon. If you have a carbon leaving group bond where it's attached to an sp or sp2 carbon, I'm going to put a circle and a cross through them. You will see no SN2 reaction. So it's important that for an SN2 reaction, as well as some other substitution and elimination reactions that we're going to talk about, the leaving group must be attached to an sp3 carbon in order for the reaction to occur. Finally, an SN2 reaction is product favored if it makes the weakest nucleophile, which is generally going to be the weakest base. So we can use our tool of the pKa table to get a sense of leaving group strength. Generally, a good leaving group is a weak base, while good nucleophiles are usually strong bases. So for example, halides and sulfonic acids are great leaving groups. Water is an okay leaving group. When you move on to more basic, more nucleophilic species, hydroxide, alkoxides, and amides are generally pretty bad leaving groups. And you will almost very rarely ever see hydride and alkyl groups as leaving groups, because this carbon-centered anion is an extremely strong base and an extremely strong nucleophile. So you can use your pKa table to get a sense of whether a group's a good leaving group. Generally, good leaving groups are weak bases, while good nucleophiles are strong bases. So to make sure that we understand this idea, I'd like you to tell me which of the following molecules in each pair has the best leaving group. Pause the video, take a few moments to work through this, and then we'll discuss. So in this case, we have a choice between iodide and hydroxide. Iodide is the weaker base and the better leaving group. In the second case, we have a choice between hydroxide and the acetate anion. The acetate anion is the weaker base and thus the better leaving group. Good leaving groups are weak bases with stable charges. So good leaving groups have the capacity to stabilize a negative charge and stabilize electron density. Now, if you don't have a good leaving group, you can make one. Generally, protonation or activation of a leaving group with a Lewis acid makes a better leaving group. For example, hydroxide is not the best leaving group, but if we protonate our alcohol with acid, we generate water, which is a better leaving group, at least much better than hydroxide. This water leaving group can be displaced readily via an SN2 reaction. You can also facilitate and activate halogens via treatment with silver salts, such as silver nitrate. If you have a nucleophilic group, nucleophilic groups can be converted to great leaving groups, such as tosylate or mesylates. So all of these are sulfonyl chloride. These sulfonyl chloride reagents can be used to make an alkyl sulfonate, and toluene sulfonates and other sulfonate-derived leaving groups are great leaving groups. So if you have an alcohol, you can convert it to a good leaving group using toluene sulfonyl chloride and other sulfonyl chloride activating reagents. You can also, although this is less common, also make the acetate derivative, though acetate isn't nearly as good of a leaving group. So how does this work? How does this work? Well, in net, we take the alcohol, we make the alkyl sulfonate, and this group is a good leaving group. I would say even it's a great leaving group. So your nucleophile can readily displace your leaving group, and using the alkyl sulfonate is much easier than trying to directly displace an alcohol. So what's the mechanism? So first, your alcohol attacks, and you end up with an acyl substitution reaction where net you replace the sulfur chlorine bond with a sulfur oxygen bond. From here, you deprotonate your oxygen atom, and this gives you your alkyl sulfonate. When, again, as discussed, this group is a wonderful leaving group. From here, we just observe a typical SN2 reaction where your nucleophile attacks and you displace and lose your leaving group. So you can activate alcohols as leaving groups via protonation or via making the sulfonate using reagents such as toluene sulfonyl chloride and other sulfonyl chloride reagents. This group, if it's derived from p-toluene sulfonyl chloride, is called a tosylate group. So you can commonly see this entire group abbreviated as OTS, where TS stands for the tosylate. Other reagents that are used to activate alcohols are thionyl chloride and phosphorus tribromide. These are common activating reagents to prepare halogens from alcohols. In this case, the alcohol reacts with thionyl chloride and in turn makes a great leaving group that can then be displaced by the chloride anion. Same thing happens with phosphorus tribromide. You end up with formation of an oxygen-phosphorus bond. Overall, this group is a great leaving group, and it can be readily displaced by your nucleophilic halide anion. So if you don't have a good leaving group, you can make one, either by protonation, making a tosylate, or mesylate, or via using an activating reagent. So there are many ways to activate a group as a leaving group. Let's talk now about the SN2 reaction in terms of substitution and solvent effects. Increasing substitution results in a slower rate of reaction. Why? It's more difficult for the nucleophile to approach and displace the leaving group. Importantly, and I want you to keep this in mind, the SN2 reaction does not occur on tertiary substrates. It is too hindered. So if your nucleophile tries to approach, it gets blocked by the high substitution around the carbon sigma star orbital. So the more substituted your carbon becomes, the slower the rate of reaction. And if you try to run an SN2 reaction on a tertiary substrate, you won't see appreciable reaction, at least via the SN2 pathway. In terms of solvent effects, for SN2 reactions, a higher energy nucleophile generally results in a faster reaction rate. Polar protic solvents slow SN2 reactions by stabilizing the reactant nucleophile. So these kinds of polar protic solvents will interact with and stabilize your nucleophile, and in turn, that slows the rate of reaction. As a comparison, SN2 reactions are typically run in polar aprotic solvents that do not hydrogen bond. And the reason why polar aprotic solvents are typically selected for SN2 reactions is because they don't stabilize your nucleophile. They, in turn, allow for a faster rate of SN2 reaction. So here are examples of polar aprotic solvents. Let's talk a little bit about the effects of reaction condition changes on the SN2 reaction coordinate. The SN2 reaction coordinate is a single step. The SN2 reaction is a single step. And as we discussed, as substrate hindrance increases, the rate of reaction slows. This is because the activation energy increases, which in turn decreases the rate of reaction. So if you have a hindered substrate, it will be a slower reaction compared to an unhindered substrate. This explains the observed trend of reactivity in SN2 reactions, where primary substrates react faster than more substituted secondary substrates. So if we had to select which substrate will have the fastest rate of SN2 reaction, a primary or a secondary substrate, I'm going to 100% pick the primary substrate. Now, in terms of nucleophile effects, better nucleophiles are high in energy, and that in turn decreases the activation energy and increases the reaction rate. As we can see here, if we have a good nucleophile, your reactants are higher in energy, and so your Gibbs energy of activation is going to be small compared to if you have a poor nucleophile that's low in energy, where the Gibbs energy of activation is large. So for the SN2 reaction, for a quick, fast SN2 reaction, you want a high energy nucleophile, a strong nucleophile, because that gives the lowest activation energy and the fastest rate of reaction. So if we have a choice between an alcohol and an alkoxide anion, I'm going to pick the alkoxide anion because it is the stronger nucleophile and thus would yield a faster SN2 reaction. Stronger nucleophiles have the faster rate of SN2 reaction. As we discussed in terms of solvent effects, polar protic solvents stabilize the nucleophile, giving a larger activation energy and a slower rate of reaction. So if we had a choice of which of these two solvents would best facilitate a fast SN2 reaction, we can either choose a protic or an aprotic solvent. And as we discussed, the polar aprotic solvent, such as tetrahydrofuran, would yield the faster rate of SN2 reaction because we are not excessively stabilizing our nucleophile. The nucleophile remains high in energy. We have a lower activation barrier and in turn a faster rate of reaction. Let's talk about some other effects on the reaction coordinate if we change the reaction conditions in the SN2 reaction. So let's talk about the leaving group now. Good leaving groups result in a lower activation energy as the product energy is slightly lower. So when we think about what happens with our leaving group, and if we think about the transition state for a moment, in the transition state, we're forming a bond between our carbon and our nucleophile and breaking the bond between our carbon and our leaving group. This step overall is exergonic, so your transition state is going to resemble your reactants. The better your leaving group is, the easier it is to break this carbon leaving group bond. And in turn, because it's easier to break this carbon leaving group bond, that in part contributes to the fact that the activation energy is lower when you have a good leaving group. So, good leaving groups have a lower activation energy. And so, for example, if you have a choice between picking which of these two substrates will have the faster rate of SN2 reaction, the substrate with the alkyl iodide has the better leaving group and thus will have a faster SN2 reaction. So let's now practice drawing out some reaction coordinates. And I'd like you to try to draw the reaction coordinate comparing the following two reactions. So these are both SN2 reactions. And in this case, looking at some differences here, we see that the major difference concerns the solvent. So here we have a protic solvent versus an aprotic solvent. So take a few moments with that initial observation in mind, and I'd like you to draw a reaction coordinate for each of these two SN2 reactions and compare these two SN2 reactions. So pause the video and we'll discuss momentarily. Okay, so first and foremost, I'm going to label these reactions A and B. Let's use some different colors for that. So in reaction A, we're going to have our reactants. And if we think about our reactant energy, because we have an aprotic solvent, we're going to have a relatively high energy nucleophile. There's going to be a transition state. In this transition state, we're going to be forming the bond between our carbon and nucleophile and breaking the bond between our carbon and leaving group. Then we will get our product, which will have a new bond between our carbon and our nucleophile, and we'd lose our leaving group. Okay, by contrast, if we change our solvent to a protic solvent, that's going to lower the reactant energy because our nucleophile is stabilized. What that means is, because we're getting to the same transition state, let me just make sure to draw this so that they're the same height. The transition state is going to be exactly the same. The main difference is our Gibbs energy of activation, our activation barrier, is going to be larger. So we can say that reaction A will be a faster SN2 reaction. So again, the only difference between these two reactions is the solvent. When you use a polar protic solvent, that stabilizes your nucleophile, which in turn increases your activation energy. So reactions using a polar protic solvent for the SN2 reaction will have a slower rate of reaction, all things being equal. Likewise, reactions run in polar aprotic solvents will be faster by comparison. Wonderful. So we've learned about the effects of changing reaction conditions on the SN2 reaction coordinate, and we've practiced drawing some reaction coordinates. Let's talk about the SN2 reaction in the context of cyclic systems. So SN2 reactions are faster when the leaving group is axial. So if you have a nucleophile and it attacks and displaces your leaving group, this displacement reaction, even though we draw it with pen and paper with just a set of arrows, when we consider that we're dealing with a cyclohexane, the two conformations of cyclohexane will have different rates of SN2 reaction. And SN2 reactions are faster in the conformation where the leaving group is axial. Why is that? When the leaving group is axial, the nucleophile can approach the sigma star orbital without a ton of hindrance. Compared to if we have the leaving group in the equatorial position, your nucleophile's approach runs into hindrance by the ring. This is a hindered approach. Now, if you just have one substituent, then this subtlety can have an effect. We do have to note that the conformation with the leaving group axial is going to have a faster rate of SN2 reaction. When you start to add multiple substituents, we can start to see that this requirement and this preference that your leaving group is axial starts to have a huge impact on the rate of SN2 reaction. That's because the conformation with the leaving group axial can be very difficult to access in some cases due to diaxial strain. Thus, if you have two molecules, the molecule with the lowest energy conformation with the leaving group axial will react faster. So if we have these two molecules that I'm going to call A and B, these are stereoisomers of one another, One stereoisomer is going to exhibit a faster rate of SN2 reaction. The reason being is that if we look at the conformation where the chlorine is axial, we have this tert-butyl group equatorial. So this is a relatively low energy conformation. By comparison, in molecule B, in stereoisomer B, when you place the chlorine axial, you're forced to place the tert-butyl group axial. This conformation is high energy, and what that means, it is hard to place the chlorine axial, which gives a slow SN2 reaction. So if you have two molecules, the molecule that can more readily access the conformation where the leaving group is axial will have the faster rate of SN2 reaction. Okay, so let's try to practice what we've learned, and I'd like you to draw the products of the following reaction in dash wedge notation and as a chair conformation, and I want you to draw the mechanism. So pause the video, take a few moments, and then we'll discuss. So in this case, in the SN2 reaction, we already have our leaving group in the axial position. Your nucleophile will attack. You break the carbon leaving group bond, and that in turn gives inversion of our stereocenter. Drawn out another way, this iodine is axial pointing up, so it gets a wedge. Your nucleophile will attack, displace the leaving group, and we get the product with inversion of stereochemistry. Wonderful. Let's keep going now. We're now going to talk about a type of reaction that is, for all intents and purposes, an SN2 reaction. The kinetics are slightly different, but we're not going to worry about that for now. So let's talk about intramolecular SN2 reactions. So nucleophilic substituents such as halogens, carboxylic acids, alcohols, and amides can react via intramolecular SN2 reactions. Intramolecular reactions are generally quite fast. So in this intramolecular reaction, your nucleophile attacks and displaces the leaving group. So the nucleophile and leaving group are in the same molecule. This allows us to form cyclic systems. Now, in terms of what's happening here, and in terms of making sure your stereochemistry is accurate, because the SN2 reaction entails inversion, this stereocenter starts as S. By the end of this reaction, we get this product out. And taking a look at another way to draw out this product, we see that our stereocenter post-SN2 reaction is an R stereocenter. So we observed inversion of stereochemistry. You can also make a model, as I've shown, where I set up my substituents in a chair-like conformation and showed the displacement of the leaving group by my internal nucleophile, which is this alcohol-oxygen lone pair. Another way to draw out this product is if this iodine starts with a wedge, after displacement, the oxygen would approach from the opposite face, so it would have a dash. That's another way to draw this out. and it also works just as well. We can verify that this is true by checking the stereochemistry. If we draw the rotated form, as you can see, the stereochemistry is R at this position. So these are two ways of drawing out intramolecular SN2 reaction products. I'd say the easiest is what if you start with a dash or wedge for your carbon leaving group bond, just draw in the new carbon nucleophile bond and invert the configuration. So if I started with a wedge, I draw my product with the carbon oxygen bond being dashed. Let's practice what we've learned and let's approach the following problem. For those curious what the sodium hydride is doing, it's just going to deprotonate our oxygen atom. So in this case, I'm going to number my carbons. So 1, 2, 3, 4, 5, 6. I'm putting oxygen as number 1 because this is going to eventually be part of my ring. Because I have some sodium hydride floating around, I'm going to pull off this proton, and that in turn gives me this much better nucleophile. Remember, because it has a negative charge, it's a much better nucleophile. From here, my nucleophile is going to attack, and we're going to break the carbon-leaving group bond. Following the rule that I discussed, because the iodine started with a dash, the carbon-oxygen bond is going to get a wedge. Just as a check, this is going to be an R stereocenter because it's the opposite to this S stereocenter reactant we looked at previously. And in the product, we have an S stereochemistry. So this SN2 reaction occurred, we got inversion of stereochemistry, and all is right with the world. So we've gone through some examples now where we drew out some intramolecular SN2 reactions, very useful to form rings. Let's now try to approach the following problem, where we're asked to predict the product of the following reaction. This triethylamine is just serving as a base. Your internal nucleophile is going to be this amine here. So pause the video, take a few moments to work through this example, and then we'll discuss. So in this case, our nucleophile is going to attack the electrophilic carbon, and we're going to break the carbon-leaving group bond. Numbering 1, 2, 3, 4, 5, 6. This is going to be another 6-membered ring. Because we started with the carbon-leaving group bond dashed, the carbon-nitrogen bond will be wedged. As a cleanup step, the triethylamine will pull off a proton, and that will give us our neutral product. Just as a check for your reference, we have an S stereochemistry here, while this stereocenter is initially R. So we did observe inversion of stereochemistry. Wonderful. So we've talked about the SN2 reaction and intramolecular SN2 reactions. Let's now talk about an interesting quirk related to the SN2 reaction, which is this idea of anchimeric assistance or neighbor group assistance. So if a nucleophile is adjacent or near a leaving group, an intramolecular SN2 reaction can occur. The resulting cyclic product can then be attacked by a second nucleophile in a second SN2 reaction, giving an SN2 product with net retention of stereochemistry. Anchimeric assistance is often the cause of a lot of head scratching when you run a reaction that you expect to see inversion of stereochemistry and you somehow observe retention. Whenever this kind of thing happens, you should immediately start thinking that maybe your neighboring groups are engaging in anchimeric assistance and engaging in intramolecular SN2 reactions. So the classic example of anchimeric assistance is if you take this alkyl halide and treat it with sodium acetate, you get clean inversion. If you try this same reaction on a substrate with an internal alcohol, instead you observe retention of configuration. This is the key signpost that anchimeric assistance is occurring because the SN2 reaction occurs with inversion of stereochemistry. The only way for you to see retention is either you're not going through an SN2 reaction or you're getting SN2 reaction followed by a second SN2 reaction. Two displacements yields retention. So what's happening? Well, in order for this to happen, the substituents must be trans or have the correct geometry for SN to attack. Additionally, the molecule must be in the correct conformation for the desired SN2 reaction. So in the first step, in anchimeric assistance, you see an intramolecular SN2 reaction. So this conformation is a no-go because you can't access the sigma star. So you must be in the trans diaxial conformation. From here, the sigma star is readily accessible, so your nucleophile attacks and displaces the leaving group. So this is our first SN2 reaction, and this yields this intramolecular SN2 product. Now, if you didn't have a nucleophile floating around, this is where the reaction would stop. But usually if you're trying to run an SN2 reaction, you have a nucleophile floating around, and that nucleophile will attack and displace your newly formed, in this case, carbon-oxygen bond. So we have a second SN2 reaction where this SN2 reaction occurs to open up the ring. This yields inversion of this stereocenter and net retention overall. So if we were describing this from a dash wedge perspective, we would have the following product. So as you can see, we end up with an intramolecular SN2 reaction followed by an intermolecular SN2 reaction. Two SN2 reactions yields a net retention of stereochemistry. As you can see how this stereocenter has a net retention. Okay, so this is how anchimeric assistance works. You always need to be wary of anchimeric assistance if you have nucleophilic groups in your molecule. This comes up a lot in the context of sugar chemistry and other complex molecules. The key point for anchimeric assistance, it's still fundamentally SN2 reactions. You just have a set of SN2 reactions occurring one after another. Okay, so we talked a lot about the SN2 reaction. Let's talk about the counterpart to the SN2 reaction, which is the SN1 reaction. As its name implies, it's a first-order unimolecular nucleophilic substitution reaction. The SN2 reaction requires an sp3 carbon. So what's the mechanism for the SN1 reaction? The SN1 reaction involves loss of the leaving group to yield a carbocation. This is the rate limiting step. And then the carbocation is attacked by the nucleophile. So in the first step, you break your carbon-leaving group bond to make a carbocation intermediate. And in the second step, the carbocation is attacked by the nucleophile. Now, because we go through a carbocation, we inherit all of the problems with carbocations. Because the reaction proceeds through a carbocation, we observe a mixture of stereoisomers, because the carbocation can be attacked by the nucleophile from either face. So, with this in mind, let's try to draw a mechanism for the following SN1 reaction. So in this case, in the first step, we break the carbon-leaving group bond. That in turn generates a carbocation. From here then, the carbocation is attacked by the nucleophile. That in turn forms a new bond between the carbon and our nucleophile. Then, often as a cleanup step, either a molecule of reactant or a base that is available floating around in solution will come in and deprotonate your reactant, or will come in and deprotonate this product and generate the neutral product. So again, in the SN1 reaction, your leaving group leaves to make a carbocation. The carbocation is attacked by your nucleophile. And from there, you usually have a cleanup step, which is a deprotonation step, just to get a neutral product. Okay, let's keep going now, and let's talk a little bit about the kinetics and reaction coordinate for the SN1 reaction. So the SN1 reaction rate law is first order in substrate. The rate depends only on the substrate concentration. It does not depend on the nucleophile concentration. This makes sense considering the reaction mechanism notes that carbocation formation is the supposed rate-limiting step in the reaction mechanism. The SN1 reaction rate is highly sensitive to the leaving group, but it is not sensitive at all to the nucleophile, not to an appreciable degree at minimum. This makes sense because the key slow rate-limiting step is breaking this carbon-leaving group bond to form the carbocation. Once you have the carbocation, it'll react with pretty much any nucleophile as long as it's a remotely competent nucleophile. In terms of the reaction coordinate, the SN1 reaction coordinate, the SN1 reaction is a two-step reaction, which goes through a carbocation intermediate. Carbocation formation is the rate-limiting step. So in the first step, we break the carbon-leaving group bond to make a carbocation. This is rate-limiting. And in the second step, your carbocation intermediate reacts with the nucleophile to form the carbon nucleophile bond. So how is the SN1 reaction sensitive to substituents? Because the rate-limiting step in the SN1 reaction is carbocation formation, the more stable the carbocation formed, the faster the rate of SN1 reaction. This explains why tertiary substrates have particularly fast rates of SN1 reaction, while primary substrates have functionally very, very slow rates of SN1 reaction to the point where you will not see SN1 on primary substrates. The other thing I'd like to note is that allylic and benzylic substrates have relatively fast rates of SN1 reaction because you generate a highly stabilized carbocation. So one thing I'd like you just to always keep in mind is methyl and primary carbocations are so unstable that they are not usually formed. Please do not draw primary carbocations unless they're allylic or resonance stabilized. So let's take a look and let's ask which of the following compounds will have a faster rate of SN1 reaction, given that SN1 reaction rate increases the more stable your carbocation formed will be. So if we have a choice between a secondary and a tertiary substrate, the tertiary substrate is going to have the faster rate of SN1 reaction. By comparison, let's now look at this next case where we have two compounds and we're trying to determine which of these compounds will have the faster rate of SN1 reaction. In this case, let's draw the carbocation out. So here, if we look at this carbocation, we can delocalize our positive charge to a tertiary center. While in the following compound, taking a look at this carbocation, we can only really delocalize it to a secondary or a primary center. So the compound on the left, overall, you can make a more stable, resonance stabilized carbocation. You can not only delocalize your charge across multiple atoms, but you can place your carbocation on a more stable tertiary position. So this compound on the left will have a relatively fast rate of SN1 reaction. Key thing I need to impress on you, you have to consider carbocation stability when you think about the SN1 reaction, and you have to draw the carbocation to truly get a sense of how stable that carbocation is. Now, as mentioned, allylic and benzylic substrates have really fast rates of SN1 reaction because you have a stabilized carbocation. Allylic and benzylic carbocation intermediates are stabilized by delocalization of the charge. As a consequence of that, regioisomers can be observed for the SN1 reaction. So when you have an allylic halide, you'll get a mixture of products. Where do those two products come from? Well, you have two possible carbocation intermediates. You can have a carbocation at what I'll arbitrarily call carbon 3 versus carbon 1. And these two products are unique regioisomers. So when you have an allylic alkyl halide and it reacts via an SN1 reaction, because your carbocation can be delocalized across multiple atoms, you'll observe a mixture of regioisomers. So because the SN1 reaction goes through a carbocation, it inherits a lot of the issues with going through a carbocation. It's a little harder to control SN1 reactions compared to the SN2 reaction. Let's talk now about the SN1 reaction and the leaving group. The rate of SN1 reaction increases if the substrate has a good leaving group, because it'll be easier for you to break that carbon leaving group bond and make your carbocation. Good leaving groups are weak bases or large atoms that can readily stabilize electron density. One way to activate your leaving group is under Bronsted acidic conditions. Leaving groups can be activated via protonation. So you can protonate your alcohol, and that makes a better leaving group. By the same token, coordination of a Lewis acid to a Lewis basic lone pair can activate a leaving group for elimination or substitution. So for example, if you treat an alcohol with aluminum trichloride, you can in turn coordinate your lone pair, and this makes a better leaving group. So, to this end, let's take a look at the following molecules, and I'd like you to tell me for each pair, which of the following compounds will have a faster rate of SN1 reaction. So in this case, we have a choice between a hydroxide leaving group or a trifluoroacetate leaving group. The trifluoroacetate leaving group is the better leaving group. And because it's easier for the leaving group to leave and for us to make a carbocation, this substrate on the right will have the faster rate of SN1 reaction. By the same token, if you have water as a leaving group versus hydroxide, water is the better leaving group, and thus you would expect this compound on the left to have a faster rate of SN1 reaction. To make sure we're comfortable with drawing SN1 reactions, I'd like you to try to draw a mechanism for the following reaction and predict the products from this reaction. So pause the video, take a few moments to work through this example, and then we'll discuss. So in this case, first and foremost, hydroxide's a terrible leaving group, so our leaving group's going to be activated via protonation. This is an idea that we discussed. Now we have this great leaving group, and we can make a tertiary carbocation. So our leaving group is going to leave. This generates a carbocation. Now, pretty much any nucleophile, even a terrible nucleophile such as chloride, can go in and attack our carbocation, and that in turn generates our alkyl halide product. So, in the SN1 reaction, you end up with loss of your leaving group to form a carbocation, and then the carbocation gets attacked to form a bond between carbon and your nucleophile. Okay, let's keep going now. Let's talk a little bit about the SN1 reaction in terms of solvent effects and nucleophile effects. So the rate of SN1 reaction increases if a polar protic solvent is used. The reason why this occurs is that polar protic solvents can stabilize the carbocation and facilitate carbocation formation. So here's what the reaction coordinate looks like. If you use a polar protic solvent, you can stabilize your carbocation. As you can see, we have a more stable carbocation. And as a result, if we look at this activation energy, we have a lower activation energy. With that information in mind, take a moment and tell me which of the following solvents would promote a faster SN1 reaction. So we have a choice between methanol and acetone. In this case, methanol is a protic solvent, so we'd expect the polar protic solvent to have the faster rate of SN1 reaction. Let's now talk about nucleophile effects for the SN1 reaction. As discussed, the rate-limiting step in the SN1 reaction does not involve the nucleophile, and as such, the rate of SN1 reaction does not depend on the nucleophile. One benefit of this is the SN1 reaction allows the use of relatively bad nucleophiles as the carbocation is so reactive. If allowed, nucleophiles can be used as the solvent or in large excess. For example, one common reaction is known as solvation. This is still an SN1 reaction, except your nucleophile is used as the solvent. The mechanism is still the same. You break your carbon leaving group bond, you generate a carbocation, and here your solvent doesn't just stabilize the carbocation, it also acts as the nucleophile, attacking your carbocation. So usually for the SN1 reaction, if you can, it's often easy to make the nucleophile your solvent. Just allows you to avoid some unfortunate side issues that can occur. Key point, SN1 reaction doesn't really depend on the nucleophile at all. It allows us to use very bad nucleophiles and still get a reasonably efficient SN1 reaction. Let's talk a little bit about some special cases for the SN1 reaction. One special case is this idea of anti-aromatic carbocations. So anti-aromatic carbocations usually do not form. So anti-aromatic carbocations have 4n pi electrons. So for example, the carbocation derived from cyclopentadienyl chloride, this carbocation is anti-aromatic, and thus it's not favored to form. And thus you will see a very slow SN1 reaction, if at all. As a corollary, aromatic carbocations form readily. These have 4n plus 2 pi electrons. So for example, this carbocation, which is the tropylium ion, has 6 pi electrons, and this carbocation formation is very fast, so you will see a very fast SN1 reaction. So anytime you see a situation where your SN1 reaction is unusually fast or unusually slow to the point where it may not even occur, usually you're dealing with some sort of aromatic or anti-aromatic carbocation species. It is hard, if not impossible, to make anti-aromatic carbocations quickly and efficiently. As a counterpoint, aromatic carbocations form readily. Another special case to keep in mind are bridgehead carbocations. Bridgehead carbocations and alkenes usually do not form. They don't form. This is known as Brett's rule. There are exceptions, but in general, if you have a bridgehead and you're trying to form a carbocation at the bridgehead, it is way too strained. Make a model or try to make a model of this, and you will see that these kinds of bridgehead carbocations, where you have an sp2 carbon at a bridgehead, are very strained. What this means is you will see pretty much slow or no SN1 at bridgehead carbons. One other consequence of the SN1 reaction going through a carbocation is that the SN1 reaction is susceptible to carbocation rearrangements. So, given that we talked about carbocation rearrangements previously, let's try to draw a mechanism to explain how you start with your leaving group on this carbon, and somehow you end up with your nucleophile on the adjacent carbon here. I'll give you a hint, it involves an alkyl shift. So pause the video, work through this example, and then we'll discuss. So first, as with any step in the SN1 reaction, we are going to lose our leaving group. From here, we're going to see an alkyl shift, which in turn generates the more stable tertiary carbocation. From here, Your nucleophile attacks the carbocation. And as a cleanup step, we're just going to deprotonate. Let's draw that arrow a little bit more nicely. There we go. And that in turn generates our SN1 product after a carbocation rearrangement. Wonderful. So key thing, SN1 reactions go through carbocations. As such, you have to be wary about carbocation rearrangements. Now, we have these two possible substitution reaction pathways. How do we predict whether a reaction proceeds via SN1 or SN2 pathways? The first thing to look at is the substrate. Allylic, benzylic, and tertiary substrates prefer SN1 reactions. They make stable carbocations. Primary substrates prefer SN2. Secondary substrates react depending on the nucleophile and solvent. So for example, if we have this primary substrate, that's going to proceed and prefer SN2 reactions. A tertiary substrate will prefer SN1. Let's try and think about these next two substrates, and I'd like you to tell me, is this substrate going to prefer via an SN1 and SN2 pathway, or is it ambiguous? Do we need more information? Pause the video, take a few moments, and then we'll discuss. So in this case, we have an allylic substrate, and allylic substrates prefer SN1 reaction. For this secondary substrate, we need more information. We need to know the nucleophile and the solvent. Now, in terms of the nucleophile, strong nucleophiles favor SN2 reactions, while weak nucleophiles favor SN1 reactions. Note the SN2 reaction rate depends on nucleophile strength, while the SN1 reaction does not care about the nucleophile pretty much at all. In terms of solvent, polar protic solvents favor SN1. One moment. While polar aprotic solvents favor SN2. In terms of the leaving group, good leaving groups accelerate the rates of both SN1 and SN2 reaction. I would note that the leaving group often gives us the least information in terms of whether the SN1 or SN2 pathway occurs, simply because the leaving group affects the rate of both SN1 and SN2 reactions. So I made a table here where if you're wanting to differentiate between SN1 and SN2 pathways, you can look at the substrate, then the nucleophile, then the solvent. This is a summary of what we discussed. So let's try to apply what we've learned, and let's take a look at these two reactions. I'd like you to predict the products of these reactions, and I'd like you to tell me, does the reaction proceed via an SN1 or SN2 pathway? So pause the video, take a few moments, and then we'll discuss. Okay, so first and foremost, this is a secondary substrate. It's ambiguous. We have a very strong nucleophile. Sulfur-based nucleophiles are great nucleophiles. Now, we also have a polar aprotic solvent. And so given we have a strong nucleophile and a polar aprotic solvent, we're going to likely think this is going to go through an SN2 pathway. So in this case, we have displacement of our leaving group with inversion, and that in turn yields the following product. Looking at this next case, we have a protic solvent, we have a secondary substrate, and in terms of our nucleophile, we have a relatively poor nucleophile. Methanol, not the best nucleophile. So in this case, we're going to see protonation. That in turn generates a good leaving group. Because we suspect an SN1 pathway, because we have a pretty bad nucleophile and a polar protic solvent, what we're going to see next is our leaving group leaves to make a carbocation. And from here, the nucleophile will attack the carbocation and give us a mixture of stereoisomers. So what that means is, in terms of our two products, we would get a mixture of the two stereoisomers. So as you can see, one of the ways that you can differentiate an SN1 and SN2 reaction based on product outcome is the SN2 reaction occurs strictly with inversion of stereochemistry, while the SN1 reaction, because it goes through a carbocation, will yield a mixture of stereoisomers. So we've reached a good stopping point for this first half of the lecture. So we talked about all the different types of substitution reactions, SN1 and SN2 reactions, and we talked about how to differentiate SN1 and SN2 reactions. In the next part of this lecture series, we'll discuss elimination reactions and differentiating the types of elimination reactions. So we'll continue this lecture series in the following video.